Good afternoon, everyone. Thank you for joining us today for our engineering webinar, Acoustical Considerations for Building Design. My name is Tina Carroll, and I'm going to be moderating today's event. If you have any technical issues or questions, please feel free to go ahead and email me, tinac@pricehvac.com. Or you can use your chat or Q&A function right there on the right side of your screen. At the conclusion of today's presentation, we're going to open up the floor for our Q&A. But please go ahead and submit those questions during the presentation if you come up with any, and you can do this by using your chat function or your Q&A function that is there also on your toolbar. Please go ahead and address those questions to all panelists. And now to introduce our presenter for today. Our presenter is going to be Alex Mashad. Just a second. All right, Alex is a Senior Project Manager for Noise Control Solutions here at Price. Alex oversees the development and the application of components within the built environment that impact acoustics. His focus includes the complete silencer, acoustic panel, and acoustic louver product lines. He is actively engaged in industry organizations that do relate to acoustics and noise control, including ASA, INCE, and he is a member of ASHRAE Technical Committee 2-6. Now we're turning over the presentation to Alex.
Thanks, Tina. So today we're going to go over several different aspects of noise control and acoustics. And so this is the agenda. The important slide is actually going to be just one slide, so we're going to focus mainly on the other three. Again, if you have any questions, feel free to type them in, and we'll try to get to them at the end of the presentation. So the first question that often comes up is, why is noise control important? And I think this statistic helps to explain it pretty well. It's oftentimes one of the biggest issues that occupants have regarding the built environment. And so in the case of hospitals, patients find it to be far and away the biggest issue for them, even more so than the food, believe it or not. So some of you might say, well, patients they complain about everything, which might be true, but even the staff is very impacted by noise. And so a lot of this has really come about because of awareness, and a lot of this awareness has really been the result of a lot of different organizations that are made up of people both in the industry and also in academia. A couple of them are listed at the bottom, and I'm sure you're all aware of at least ASHRAE. And so they've really helped to establish sort of design guidelines and best practices for what should be done regarding building design. So a lot of what I'm talking about today is, frankly, all contained somewhere within ASHRAE. Typically, the Applications Handbook is a great resource, and it really does a good job of laying out a very clear, easy-to-follow foundation. So, but then again, even in the case of LEED now, there are points that are available, and I think this is just another good indication that the building community is finally recognizing the importance of noise and acoustics. So, like I said, that's a quick slide. Let's get into some terminology really quick for those of you that aren't as familiar about acoustics. So the first question then is, what is noise? And unfortunately, we're not doing this in a setting that allows for people to actively respond, because I've heard all sorts of interesting answers to this question. But noise simply is unwanted sound. So a lot of times this is going to be a chiller that's screaming. It's going to be an air handling unit. It's going to be a terminal that's right above you. It could also be traffic. It could also be an airplane that's flying above. And finally, it could be occupants. It could be people. So there's a lot of different types of noise sources. Another good example of a sort of noise source that a lot of people don't think about are those dryers in the bathrooms. These can get up to 95 to 100 decibels, which is incredibly loud given the space they're in, and this can ultimately impact many times adjacent spaces, such as the corridor outside, or if there's an occupied space directly connected to a bathroom. And So these types of noise sources also need to be considered. But we're going to really focus more on the mechanical, typical noise sources for today. The next kind of simple topic to quickly go over is to understand how noise transmits through air. So you're basically dealing with pressure variations, and they emanate typically from some sort of source that's oscillating. And the energy is then passed, and basically between these particles, that energy continues on until it hits either some sort of barrier or, in many cases, a person. So at the bottom there, you kind of get a visual of how these particles and the energy transfer through the air. In this example, again, it helps to show, in the case of a bell, as it's oscillating, it's then passing that energy on to nearby particles, which in turn do the same thing, and eventually it hits a receiver or it hits some sort of building element. So this is how sound, as we typically deal with it, travels, and so hopefully you have a better understanding of that. A lot of times, too, you hear sound power, sound pressure, sound intensity, so just a quick sort of easy way to understand the differences. Power is essentially, when you're thinking about a fire, it's basically like describing how much heat is generated by that fire. So there's no way to really measure sound power. Instead, we basically measure sound intensity, and then we go backwards because we know the distance from the source, and we're able to then determine the sound power of that source. And then sound pressure ultimately is typically what we're experiencing as occupants, because this is going to vary with distance. So you can imagine the same way with a fire, as you get further away from a fire, the heat decreases. And just like with sound then, as you get further from a source, typically it gets quieter. And then if you were to put a wall or some other type of building element between the source and the receiver, that pressure or that heat would be even lower. So the relationship then between intensity and distance is given here following the inverse square law. So this simply helps to describe how the intensity decreases with distance. And I think visually looking at it, it's a little more clear. So you can imagine that as you're increasing your distance, if you're doubling it, for example, then your intensity is reduced to a quarter, because effectively the area with which that energy is being dispersed has now increased significantly. Now this is the case when we talk about the free field. So with the free field, we're basically getting a decrease of 6 decibels for every doubling of distance from the source. And again, this is following the inverse square law. A free field example would be if you had an airplane, or maybe a helicopter is a better example, hovering in midair, and there's really nothing else around it, so it's just kind of a single point source. But in reality, when we think about a free field, which is shown here as an example, we don't see this too often in the built environment. So another example that's more common is this anechoic chamber, and this is used, again, to measure the power, ultimately, of these engines or various components. And so you're absorbing all of the reflections that would otherwise occur and not represent the actual power output of the equipment in question. The more common type of noise source that we see, though, is a line source. And so with this type of source, you're getting around a 3 decibel decrease for every doubling of distance from the source. And the reason for this is because the point sources are reinforcing each other. So a common example would be on a rooftop if you had a lot of equipment, or traffic would be another common example. And so you're not getting nearly the same amount of noise attenuation as you're increasing the distance. This is why if you were, let's say, in a hotel on a very high floor, you're still able to hear a lot of the traffic and a lot of the noises below, because of the simple fact that even though you might be several maybe 100 feet or more away from those noise sources, you're still not getting nearly the same amount of attenuation as you would if it were some free field condition. This is an easy chart that helps to describe the two as well. Again, if you're working on a project and you've got maybe a train track that's nearby or some other sort of source that you're concerned with, you can see that for a line source, when you're 60 feet away, for example, you're getting about a 7 dB noise reduction. Whereas if you were dealing with a single point source, now you're getting upwards of 16 dB. So that's a pretty significant decrease in noise. And again, this is across all frequency bands. So hearing range we'll talk about very briefly, but humans hear ideally between 20 and 20,000 hertz. This is pretty much when you're out of the womb. Unfortunately, shortly thereafter, our hearing typically starts to deteriorate, such that in the higher frequencies, as we get older, we often cannot hear above 8,000 or 10,000 hertz. Human speech is between 125 and 8,000 hertz, so these are the bands in which we're very sensitive. 1,000 hertz is actually where we're the most sensitive. Again, as we get older, too, the lower frequency range also deteriorates, so we can't hear that low frequency noise as well. Wavelengths, it's worth talking about briefly. So typically when you see equipment, if it has the sound power levels, a lot of times it'll have discharge noise or discharge power and radiated power and inlet power. So typically they're going to list the noise levels at these different frequencies. So the 0 through 8 just represent a common way of referring to the octave band, and then the actual center frequency is provided below. And with the wavelength itself, in yellow there, you kind of get an understanding of how long these wavelengths are. So the lower frequencies have much longer wavelengths, and this is one reason that they oftentimes are able to travel and be more disruptive because of just their natural length. And I think a good example of this is with walls when we think of their typical thickness. You can see here that a lot of walls are a lot less than 12 inches thick. They're probably 6 inches thick for interior walls. So they're more effectively able to stop the higher frequency noise in the same way that when you think about an absorptive fabric wrap panel or something too, those are a lot of times maybe 2 inches thick, 4 inches thick. Whereas again, for those lower frequencies, they have much longer wavelengths. Typical background noise, again, this is all laid out in ASHRAE applications, 48.3, but these are just some commonly accepted levels. NC is a way of describing noise levels based on how we hear things. So in the lower frequencies, we're not as sensitive, so you're able to allow for higher decibel levels. And then in the higher frequencies where we're more sensitive, basically it curves downwards because you have to have lower decibel levels. The dBA equivalents are next to the NC levels, and it's just worth remembering that there's about a 5 to 7 point difference between an NC and a dBA level. So in New York, for example, one of the code requirements is often 42 dBA, and this translates roughly to NC 35. So that's about a 7 point difference. Obviously, if there's, that's assuming a pretty standard curve. So if you had some sort of tonal noise or a strange amount of higher frequency noise, then that would not necessarily line up. And then again, how we hear, when we deal with sound, we're talking about logarithm, addition, subtraction. So humans hear things logarithmically, and this was started by Alexander Graham Bell. This is more useful maybe for trivia night, but I thought it was kind of interesting. So the Bell unit was originally used to relate intensity as it relates to human hearing. So that's how we've kind of come up with the current system. And then when we say decibel, a deci indicates a logarithm multiplied by 10. And again, the sound intensity bells is simply the logarithmic the ratio of the two intensity levels. So you have your measured on top, and then you have your reference on the bottom. If we look here, we're just comparing different decibel levels, and so 0 decibels, you're essentially at the threshold of human hearing. You can't hear anything quieter than that. So at 10 decibels, that's similar to leaves falling, and you can see as you get louder and louder, you're basically then kind of getting into environments that you're more used to, such that when you get upwards of 60, 70, you're in your typical kind of office environment. 80 is around what you hear when you're inside a car. This is also kind of a reference point that they sometimes say, if you're exposed to this for a long period of time, you can incur some sort of hearing damage. Unfortunately, you can't tell your boss that you have to stop commuting to work because this would require you to commute for more than 12 hours a day, which hopefully no one does. And then finally, when you get upwards of 150, this is kind of the threshold before you really start to, well, at this point you would start feeling pain, but the 150 is around 75 feet from a jet airplane taking off. So at these levels, you don't have to be exposed to it for very long before you start having some sort of hearing damage occur. So it's important to understand, too, that with changes in sound levels, it's highly individualized. So a lot of it is sort of a perception that is on a case-by-case basis. So it's very hard to say, what is annoying to one person or what's loud to one person is going to be the same for another person. But these are just some sort of general rules that are typically accepted in the industry. So if you have a 1 dB change, this is almost always imperceptible. It's worth pointing out that when you're talking about sound level meters, too, they have a tolerance of around 1 dB. You've probably heard the terms, class 1, class 2, class 3. When you get to about 3 dB, this is about where you can start to perceive some sort of difference. It's also worth pointing out that the testing standard for silencers, ASTM E477, in their precision and bias statement, they allow for a 2 to 3 dB tolerance, and part of it is because of the measuring tools, but part of it is, I think, because of the fact that humans, again, really below 3 dB don't notice a change. So it's worth pointing this out just because sometimes you're going to get a schedule or you're going to see some sort of requirements in the specification, and it's very easy when you're doing a review to say, okay, you're off by a single dB, so I'm going to fail you, or you're going to have to resubmit. But in many cases, this might not be, the biggest issue, and so it's worth talking with the consultant or talking with the manufacturer to really understand, is this a cause for concern or not. When you look at 6 dB, this is really where you start to clearly notice a difference, and then at 10, it's perceived as being twice as loud or half as loud, and then 20 is 4 times. Again, this is logarithmic, so then when you get a sound level change of 30 would be 8, and 40 would be 16. So really, when a lot of times, too, it's important to realize that, where you are when you're designing a building versus when you're actually going to bid or when you're going to install the equipment. A lot of times that equipment changes, and unfortunately, in many cases, it's not even available. So it's important to check the noise levels and make sure that the noise levels have not, in fact, changed. And I know a lot of times I would see equipment, unfortunately, increase the noise level sometimes by as much as 8 or 9 decibels, and again, that'll be perceived as being twice as loud, so it definitely requires some additional review. And then again, decimal addition, it's worth just touching on quickly. So the easy way to approach this is when you have 2 sources and they're the same or off by 1, you're going to add 3 dB to the higher value. So let's say you had 2 chillers that were 90 decibels. then if you added them together, you would have 93 decibels. When the two values are off by 2 to 3 dB, then you add 2 to the highest. If they're off by 4 to 8, you add 1 to the highest. And if there's a difference of 9 or more decibels, then you just take the higher of the two values. So you had two chillers again. One was 90, one was 80. Then the total sound power would be 90 decibels. And this kind of matches up well with the previous slide where you saw that if you had a 10 dB increase, that would be perceived as being a doubling or a halving. This kind of is why a lot of times if you're designing for some equipment to be imperceptible or to be inaudible, 10 dBs is kind of a good design criteria. So if you can get your equipment to be 10 dB lower than the ambient or the background noise level, then it's oftentimes sort of accepted or understood to be imperceptible or inaudible. And again, that matches up well with how decibels actually add. So we have an example here of dB addition. So she's drying her hair, and thankfully hair dryers are not this large anymore. But in this example, if each hair dryer is 90 decibels, and there's 4 of them, can anyone, which again we can't do interactive back and forth, but hopefully you're doing the math in your head right now. And so the total output of these 4 hair dryers would be 96 decibels. So again, if you took 2 pairs, so 90 and 90 would be 93, and then 93 and 93 would be 96. So it's a pretty easy way to quickly understand what your total noise level is. And this is a good way to design if you've got several pieces of equipment next to each other, and sort of design around that worst case scenario. Obviously, the chances of all your equipment running at full capacity in the worst noise scenario case is not going to happen too often, hopefully. But again, I think people typically only notice noise when it's disruptive. So unfortunately, you sort of have to design with that mindset. So we've gone over some terminology, so hopefully that helps to explain acoustics and some of the common terms. Now we're going to get into the main aspects of noise, and so we've subdivided them into 3 components: source, path, and receiver. So this is a very kind of generic way of looking at the 3 components. You have the source, which is oftentimes thought of as the equipment. You have the path, which is oftentimes the ductwork, and then you have the receiver, the guy who's working at his desk within his space. And traditionally, a lot of times, the architect is sort of the one driving what goes on in the receiver space, and then it's the mechanical engineer that is choosing the equipment and deciding on the duct layout. So unfortunately, sometimes there's a little kind of gray area in terms of who needs to look out for what. And so I think the next couple slides will help to point some of those considerations out as you're working on a job. So this is another way of looking at it. And again, looking at it in terms of source, path, and receiver, this rendering shows a lot of the different noise control tools that exist. So if we first talk about our source, this is in red. And so we've got the piece of mechanical equipment. We've got it traveling through that louver. We've got potentially diffuser noise. If we had a terminal unit above, obviously that would be a source. And then we have people talking as a source. If we look at our path in blue, there's a lot of different paths. We have the walls. We have penetrations between or through the walls. We have doorways. And then if we have non-full height partitions, that can be a path for noise. And then finally, receivers. We have, obviously just occupants in the space. But we also have to consider outside the space as well, because if you have people walking near the building outside, that equipment noise could certainly bother them as they're going nearby. So again, a lot of different kind of variables to consider. So again, these are kind of the more traditional sources when we think of a source, so a chiller and the generator. And one of the easiest ways to treat a source at the source is with acoustic panels. And so besides obviously making equipment quieter or moving it away from occupants or occupied spaces, acoustic panels are one way to really address noise because they provide absorption and they also stop noise, providing transmission loss, or STC. They come in a variety of thicknesses, materials, finishes, and it's just worth pointing out that if you haven't used these before, they typically are consisting of a solid casing, which would be facing the receivers or the occupants, and then a liner, which allows for that sound energy to pass through and be absorbed in that absorptive media. And so the lined or the perforated side would face the source. Some acoustic panels are provided with a tongue and groove joint, so the benefit here is you're getting better consistency and performance across the panel assembly. This is also true for thermal reasons. You're not having any sort of short-circuiting. Whereas if you went with an H-channel, you wouldn't have the same consistency across the assembly. So, when we're talking about a source, obviously this is what you think of for a receiver space. But again, with acoustic panels, it's worth talking about a couple ways in which you can reduce noise from a source. So the first one is with plenums. A lot of times for large air handling units, these noise sources put out a lot of both air and noise. And so one easy way to address that is to use acoustical plenums. And what that does in the bottom left there is it not only allows for a lot of noise absorption, it also allows for easy access for maintenance or cleaning. And it also comes as a rated assembly. So instead of talking or dealing with the architect and having the sheetrock guys come in and not knowing how that assembly is ultimately going to pan out, especially if there's moisture concern, you can use an acoustical panel assembly to address that noise source. Radiated noise is very common. I think a lot of you are very familiar with addressing return or discharge noise, but radiated noise is oftentimes not picked up as much. So acoustic panels are a great way of addressing radiated noise because, again, they provide that extra STC performance that an architect would require, but they can also make the space where the equipment is actually quieter because they're absorbing the noise. And this doesn't have to just happen in the horizontal orientation. It could also happen in the vertical. So imagine if you had a mechanical room or a mechanical floor. You could use acoustic panels to beef up that slab assembly if the structural engineer wouldn't allow you to pour a thicker slab. And then finally, surrounding noise sources. So there's a lot of noise sources that are outside of the building envelope, but they still need to be addressed. So a common one would be trains or maybe air traffic. And so acoustic panels can be used as a barrier to address that source and at the same time not impact how the train operates or how the airplanes fly, because obviously there's probably very little that can be done there. The second major component is the path, and there's a lot of different elements here, and I think a lot of you are very familiar with many of these, so we're going to touch on them. And again, it's worth pointing out that ASHRAE really does a great job of describing what sort of attenuation all of these provide. So the first is ductwork, and it's worth pointing out that depending on the ductwork shape, you're going to get different absorption performance. So flex duct is going to give you the best absorption, but at the same time, because it's acoustically transparent, you're basically getting all of your energy radiating through that flex duct and ultimately into the plenum space and possibly the occupied space below. So it's important to point out if that flex duct is occurring over a sensitive space, you might want to reconsider that, because you could potentially just move your noise problem from the diffuser upstream to where the flex connection occurs. Some flex duct also is not acoustically transparent at all. There's actually some flex duct that essentially behaves the same way as unlined metal duct if it's got some sort of aluminum liner that's solid on the inside. So it's important to consider that. And then as you go from left to right, you can see you're getting less and less absorption, such that when you get to that round sheet metal duct, because of the geometry, you're containing a lot of the sound energy in there. So again, on the good side, you're not getting much breakout noise from that round sheet metal duct, but on the negative side, you are containing all of the noise to within that waveguide. So you're just not getting the same attenuation you would if you used a traditional rectangular duct. So a lot of you, I know, probably ask the question, what's the difference between just having some extra duct work versus using a silencer? Why would I need a silencer? And a silencer really is necessary if you have a short run of duct between the source and the receiver. And maybe 50 years ago this wasn't the case as much, but now, with space being a premium and designs being what they are, a lot of times we don't have a lot of duct work between the source and the receiver. So when I was a consultant, a lot of times we would tell engineers that they had to provide at least 25 feet of line duct work and 2 elbows. And this is probably one reason that they hated us. And the reality is that this isn't always possible. So in this example, we're comparing 24-inch by 24-inch ductwork, and we're comparing 10-foot length. So 10-foot duct without lining, with 1-inch lining, and with 2-inch lining. And then we've also thrown in a 3-foot and a 5-foot silencer, just to sort of give you an understanding of how these compare with each other. So you can see that without lining in the mid to high frequencies, you basically get no absorption. I decided to be generous and put the 0.3 there, but if we wanted to follow significant digit rules, I guess it would be 0. Then when we add the lining, we start to get some pretty good absorption in the mid to high frequencies. You can see when you go from 1 to 2-inch, you don't really get too much difference in the lower bands. It's really in that kind of mid-frequency, 500 and 1,000, that you see a difference. Now when you look at the 3-foot and the 5-foot silencer, you see immediately that your low-frequency attenuation is better. And especially in the case of the 5-footer, across all frequency bands, you're getting a tremendous amount of absorption. So this is why silencers are used, because simply you don't have the amount of duct length between the source and the receiver to allow for sufficient absorption. So you have to go with a silencer. And again, the silencer performance data is assuming 1,000 feet per minute with a 0.07 pressure drop. Hopefully that's acceptable. I know typically when I was a consultant, we would tell people 0.1-inch pressure drop. Even though in a lot of cases, 0.2 to 0.3 is acceptable, as long as you're taking into account, of course, system effects. And again, this is all outlined in ASHRAE as well. If you have questions, they really do a great job of laying out the attenuation in regards to per foot basis and per size, because what you quickly realize is as your duct size increases, you don't get the same performance as you do for a smaller duct. So with duct silencers, there's a couple different types, and probably most of you are familiar with these. I'm just going to touch on them briefly. Rectangulars, these are your most common, and they're your lowest cost option typically. Because of the shape, rectangular duct does allow for more breakout, so there is an HTL casing option typically, and so what this does is it reduces that potential breakout noise that could occur and disrupt the space around. Elbow silencers, so these are very typical too, especially when you don't have a lot of space. And the main thing to remember with elbow silencers is you're getting some generated noise, so that should be considered. And part of this is because you can't push higher velocities through these. The drawbacks for elbow silencers then are that they can't handle some of the higher velocities, but then also there's a higher cost associated with these. But they are very useful, again, if you're dealing with very tight space constraints. Circular, again, we talked about the circular duct and how that does a great job of retaining the sound or not allowing it to break out. With our silencers, we typically see the ability to handle very high velocities. And again, because the noise is more readily contained in the duct, sometimes you have to go with a longer circular silencer to account for that. There's a couple different fill options. For your typical line ductwork application, you can just go with an absorptive silencer, so a silencer that uses fiberglass media similar to what a duct liner material would be. But then if you have applications such as healthcare or schools, these oftentimes call out unlined ductwork. And as you saw, the unlined ductwork provides almost no acoustical absorption. So in these cases, you need to use a polymer or a packless silencer. So polymer line silencer is basically where you have a thin layer of polymer, and this separates the fiberglass media from the airstream. And again, these are very common in school and healthcare applications. The drawback for these is that you're not going to get the same level of absorption as you would a normal fiberglass filled silencer, and so oftentimes you have to go with a little longer length, in addition to the simple fact that if you have unlined ductwork, you're getting no absorption out of that. Also, the price for these is typically higher because there's more material that's going into them. The other option is to go packless, and this is especially true when you're dealing with applications that might involve labs or the need to be able to clean the silencers, so maybe for some kitchen exhaust applications or fume hoods. So with these, there's no acoustic media, and you're not getting the same level of performance as you would a normal silencer. So again, unfortunately, you typically have to go with a longer comparable silencer if it's packless to get the same performance. And these also typically are more expensive because there's more material that has to go into them. They're basically using specially tuned chambers within there to achieve a lot of the noise attenuation. With the location for silencers, the big takeaway is that you want to locate them as close to the source as possible. In the case of a mechanical room, splitting the partition is preferable because it helps to reduce the breakout. I know there are cases, obviously, where you have a fire damper, so this might not be possible. In which case, if you put the silencer either right before or right after and make sure that's sealed properly, that does a pretty good job of reducing potential breakout noise. If you have a rooftop unit, then it's typically best to put the silencer out on the roof. If you do that, obviously, you might have to use a stainless steel silencer. Another option is to put it in the shaft after it penetrates through the roof. But you want to try to contain as much of the noise outside as possible because it just reduces the amount of attenuation and associated pressure drop required. Speaking about pressure drop, so typically, typical design guideline is that anywhere from 0.2 to 0.3 inches is fine. Obviously, this is going to vary depending on the system, but I think the more important thing to consider also is system effects. So ASHRAE does a great job again of describing what some of these are, but typically they say that there should be a minimum 3 duct diameters from elbows, because otherwise you start to run into turbulence and airflow issues. Again, another option would be just to use an elbow silencer in this case. With silencers, they are tested according to ASTM E477, and the latest and current standard is from 2013, so it's worth pointing out that's what the -13 stands for. Ultimately, the testing provides insertion loss in dB. It's dynamic because you're measuring it with airflow in both the positive and negative directions. So positive would be supply, where the airflow and the noise are going in the same direction, and negative would be where the airflow and the noise are going in opposite directions. Pressure drop, obviously, is going to be very important for this. And finally, generated noise. A lot of times, especially for very low noise level applications, you got to make sure that the generated noise for a silencer is not above the design criteria. Typically for a schedule, what you guys probably are used to seeing is something that looks like this, where basically you have all the performance data you need. You have the duct sizes that you've determined, and then you have the CFM, the corresponding velocity, allowable pressure drop, and the insertion loss values in octave band 63 through 8,000. So this is a very standard sort of industry-accepted way of indicating how the silencer needs to perform. And then if there's any notes, like if the silencer had to be stainless steel, or if you needed a certain flange connection, or maybe you needed a film liner, those are typically listed in the notes section. It's worth pointing out what a silencer schedule should not look like. So this is an example of one in which they decided to, instead of listing out specific octave band insertion loss data, just made sort of generic statements across the board. So I've written it out at the top: all silencers shall be selected to provide a max of NC30 in classrooms and library, NC35 in office space, etc. The point of a silencer schedule is to tell you what the insertion loss is. That is, how much noise is reduced. So again, when we talked about earlier the difference between power and pressure, it's really got to be it has to be a straightforward description of what the silencer is doing, because obviously, when you're selecting mechanical equipment, you cannot make statements such as, all air handling units shall be selected to provide sufficient, air for occupants. Or if you're a structural engineer, you can't say all structural supports shall be selected to provide sufficient support for the building, because there's no way to really work with that and make objective decisions. So again, make sure with your schedules they provide the insertion loss values, the pressure drop, and the corresponding velocity. In terms of ductwork then, kind of some conclusions we can draw. 1-inch lining is typically good enough. Again, the 2-inch versus 1-inch didn't have a huge difference in terms of insertion loss performance, especially in the high frequencies. They were identical. In the low frequencies, they were very close. And also, if you have a few elbows in there, that's typically more than enough to make up for the difference. Again, a lot of consultants are going to tell you need a certain amount of duct work and 2 elbows before the diffusers. But again, if you can't do this, then that's where a silencer is often required. And finally, just make sure that the data provided for a silencer and listed on the schedule gives you the octave band insertion loss data, again, between 63 and 8,000 hertz, the pressure drop, and what the airflow is. Another path that is often kind of overlooked is flanking noise, or it starts out a lot of times as radiated noise, and so air transfer silencers are an easy way to sort of address this. In the rendering on the left, you see 2 common examples. So one is where you might have a full height partition, but you need some kind of airflow. Mechanical space is a good example where you might want to put a louver in the door, but that ends up just allowing all the noise to escape. So you can put an air transfer silencer above the finished ceiling to get that airflow and still come close to getting that rating that the partition needs. Another example is when you have a non-full height partition between 2 occupied spaces, so you'll have noise flanking between the 2 spaces. A third example is if you had a terminal unit in a common return plenum, and the noise from the terminal unit, the radiated or inlet noise, if it were near an open return grill, that noise would easily just go right into the occupied space. So there are products out there that can be used in conjunction with grills and diffusers to reduce this noise transfer that occurs. Acoustic louvers are another kind of tool or trick that can be used to reduce noise in lieu of a traditional louver and in lieu of a silencer. A silencer typically goes down to around 24 inches in depth or length, whereas acoustic louvers can go down to 6 inches. So these are great for facade applications or applications where you just don't have the space to use a silencer. They give you typically an 8 to 10 dB reduction. It's just important to realize that your airflow is typically limited to around 500 feet per minute. These typically come in a variety of materials and finishes, and it's important to make sure that they're AMCA certified because this allows for a kind of industry standard and accepted way of comparing the performance. Otherwise, what you see a lot of times is manufacturers will tell you what the noise reduction is. And so what they're doing is they're taking the insertion loss value of the acoustic louver and they're adding 6 decibels to it because they're saying, well, you know, you're not going to push an acoustic louver up against a piece of equipment and then you're not going to have a person pressing their ear against the other side. So in effect, you're getting a noise reduction and you're getting more than just an insertion loss sort of performance out of that louver. So again, that's just going to increase all of the insertion loss values by 6 dB when you do that typically. So again, with the path, there's a lot of different considerations, and they're all sort of summarized in this rendering. So if you have an air handling unit, of course you need to address the return and the supply noise, typically with silencers as close to the source as you can. But then a lot of times the radiated noise can be addressed using acoustic panels, whether it's vertical or horizontal. Acoustic louvers are oftentimes called out in the drawings. Sometimes architects don't know they need an acoustic louver, but they want a louver. So this is a great opportunity to use an acoustic louver if it's necessary. And then finally, air transfer silencers. A lot of times these are overlooked as well. But if you have a common return plenum, you need to just remember that it's very easy for equipment noise in the ceiling space to pass right through that opening and potentially disturb occupants below. Another component of the path is slabs and partitions. So really quickly, STC, this is basically a lab rating that's telling you the reduction in noise between incident sound and transmitted sound. The important takeaway here is it's a lab rating, so you're assuming a perfect scenario. What occurs more often is not an STC rating, and again, it's worth pointing out that STC approximates to a dB reduction. So if you hear someone say this wall is STC 50, that's about a 50 dB reduction. So if you had equipment that was, say, 95 dB and you had an STC 50 wall, you can do the quick math there, then you're at about 45 on the other side of that. But I think the more accurate way of looking at how a slab or how a wall performs in the field is ASTC. And this is a field rating that's typically 5 to 8 points lower than STC because of things like what's pictured on the right. So if you have electrical outlets, for example, or piping penetrations or ductwork, all these things are going to reduce the rating of that wall. So unfortunately, while the architect might call out for STC this and STC that, the reality is that the performance in the field is going to be 5 to 8 points lower. So just remember that when you're selecting equipment and try to kind of factor in a little safety margin, because otherwise it will be noticeable once everything gets installed. It's also worth pointing out that operable partitions are typically 10 points or more lower than what the STC rating is, because again, there's moving parts, and so for one, they're oftentimes not even installed correctly, but then even if they are, a lot of the gasketing can easily either not engage properly or be damaged over time. A couple quick scenarios for what you might see in a mechanical room. For example, if you had a louver and a door, you want to avoid this and again use some sort of air transfer silencer above. If you had some sort of penetration through a wall, you just always want to make sure that it's packed with batt and completely sealed with caulking. And then if you had an undercut for a mechanical room, this is easily addressed using an automatic drop seal. And kind of an interesting number is 1%. If you have 1% open area, you're effectively limiting yourself to around a 20 dB reduction in noise. So you can imagine if you had an STC 50 assembly and even your door was rated, but you had a small gap, maybe at the undercut or somewhere where the frame met the door, you would essentially limit the entire assembly to a 20 dB reduction, which is very little. So it was 80 decibels inside the mechanical room, it would be 60 outside, and you know, unless it's leading directly to the outdoors, that would be unacceptable for an indoor space. So we've gone through the source and the path, and the last portion is the receiver. And most of this is, again, typically dictated by the engineer, I think, or sorry, by the architect. I think the one area that you can help to influence the design is early on. When you're looking at the layout with the architect, it's a good idea to understand what the different noise levels are. And again, this is outlined by ASHRAE, but this is a good example of where you can quickly get a feeling for if you might have a noise issue. So red is NC40, yellow is NC35, and green is NC25 to 30. And you know, some typical rules that you want to follow. One, you don't want to have spaces adjacent to each other that have more than a 5 or more than a 10 NC point difference. Otherwise, you're going to probably have an issue for the quieter space. You also don't want to locate quiet spaces near equipment, such as indicated here. So you have some spaces adjacent to the elevator shaft. I worked on a job where they had the option of either building a conference room along the facade or adjacent to the elevator shaft. And they chose the elevator shaft because they thought that the sirens from Times Square would be more problematic to handle. But unfortunately, that's higher frequency noise, so it actually would have been easier had they gone that route. So instead, they went next to the elevator shaft, and try as they might, we were never able to fully eliminate that noise. So it's just important, again, to consider where your spaces are and what they're next to. In terms of terminals, a good rule to follow is, you know, radiated is oftentimes the most problematic, and typically you don't want to locate these above occupied spaces. Again, otherwise you might want to use an air transfer silencer. And again, too, we're seeing more and more designs where architects are not using finished ceilings. So it's good to point that out because AHRI and other standards typically account for some sort of ceiling effect, which ultimately reduces the noise. So when you have an exposed condition, you're going to potentially have some noise issues because you're not getting that attenuation. So finally, really quick, let's go through a couple quiet HVAC systems or alternatives to your typical VAV setup. I've been told I only have 3 minutes, so I'm going to blow through this. But again, if you have more questions, we have a lot of experts here that can help answer them more in depth. First is quiet terminals. These are options where you have a VAV and system and you want to locate terminals above an occupied space. So the quick and dirty on these is you're combining a terminal unit with a silencer, so you're addressing both your discharge, your radiated, and your inlet noise. And these are especially useful, for example, if you have a Class A space and you need to achieve NC40 and below directly below these, you're able to do so. Another system that's very quiet is underfloor. These are great for performance spaces. Basically, you're pressurizing a plenum anywhere from 12 to 14 inches in depth. And because the raised floor has a lot more mass and transmission loss performance versus an ACT ceiling, you're able to achieve a lot lower noise levels. Displacement ventilation. This is a sort of fancy term for using a traditional system but slowing the air down and introducing it at a greater kind of delta versus a traditional VAV system. So basically, you're moving air in such a way that you're taking advantage of temperature stratification, and in many cases, you're introducing that air at a very low velocity, sometimes around 40 feet per minute, and you're also doing it at a low elevation, around 6 feet and below, kind of that breathing zone. And then ultimately, because of the thermal plume from occupants, you're able to then move that air out of the breathing zone. This is really good for if you're dealing with a large space that has a very high ceiling, especially like an airport where you need to address a large volume of air, but you don't want to have to pay for conditioning all of it. So again, this just shows 2 examples in a cafeteria and a classroom. So you can see they're very non-obtrusive, and again, you're moving air in such a way that you're also achieving very low noise levels, which oftentimes classrooms require. And then finally, hydronic systems. This is just using radiant technology. So there's two basic designs. There's a panel and there's a sail. The sail is more effective because you've increased your surface area. You've also allowed yourself to take advantage of basically having the natural convection occur where the air is rising, you're getting the buoyancy, and then once it comes in contact with the cold heat exchangers above the sails, that dense air drops back down. And these are great for a variety of climates, and you can again have these both in hot and cold applications. And instead of using air, you're using water, which is more effective. And then just some quick examples here. You have both modular and linear panels. So modular is typically for the inside of the space. Linear is around the perimeter. And this is kind of similar to your fin tube or baseboard applications. The benefit, though, again, is you're not giving up usable floor space as you would with those kind of floor systems. So in conclusion, we went over why noise is important, some relevant terminology, a couple of the main aspects of noise, and finally breezed through some quiet systems. So with that, I will hand it back over to Tina.
Thank you, Alex. Thank you for that presentation and getting all of that information out. We're now going to go ahead and open up the floor for Q&A. I do have Tim Simcoe with us today. He is another product specialist with noise control, so he will be helping us filter through some of the questions. I'm going to go ahead and get right into our first question. Alex, this is for you. For typical HVAC measurements, what type of instrument do you recommend?
You know, there's a lot of choices out there. Probably a lot of people have the apps on their phones. I know I have, I think, 5 on mine. The drawback of that is they're not necessarily the most accurate. You couldn't use them certainly in court. But honestly, they are accurate enough for most instances to where you can at least get a reasonable understanding of what the noise levels are. The drawback is typically they don't give you octave band data. When I was a consultant, we typically used a B&K sound level meter. The drawback for those is they cost upwards of $20,000, so they're not kind of, you know, really a good option if you're just wanting to get a quick measurement. There are some cheaper options out there that I'm, you know, happy to kind of get into detail offline if you're interested. But again, a lot of the phone apps are a reasonable way of measuring noise, and there's actually an app specifically, RTA Lite, and I think Audio Tools is the version that costs like $19.99. But if you get an external mic hooked up to your iPhone, you can actually get pretty accurate results to within, you know, 1 or 2 dB versus a $20,000 sound level meter.
Thank you, Alex. The next question is for Tim. Tim, what is HTL casting? And along with that question is, what is the breakout noise?
That's a very good question. HTL casing stands for high transmission loss, and really what it amounts to is added mass to either the ductwork or the silencers or both. The reason why it's important is when you're dealing with breakout noise, for example, if you have sound energy contained inside of a duct traveling from a piece of equipment to the occupied space, not only do you get a certain amount of attenuation due to the duct configuration, but a certain amount of that sound energy radiates or vibrates through the casing wall. So in order to contain that, so for example, if you have some ductwork that's running from a mechanical room over top of an occupied space, and you're worried about the sound levels within that occupied space, you want to make sure that there's enough mass in that casing of the ductwork and or silencer to prevent that breakup from occurring, and thereby making an uncomfortable environment.
Thank you, Tim. Unfortunately, we don't have too much time, so I'm going to ask the last question, and any of the questions that we weren't able to address today, we will send out in a follow-up email so that you will have those resources. The last question, Alex. Are there ceiling height limitations for radiated ceilings?
Good question. There are, and typically for those types of systems, they say that 14 feet is kind of the limit. Above that, they derate the performance. So essentially, you could imagine you'd have to increase the surface area to get the same performance. That kind of cuts off around 20 feet, and once you get above 20 feet, you want to start considering alternative systems such as displacement, because essentially you're trying to condition too large of a space, and it's not a very efficient way to heat or cool a space. So again, 14 feet is kind of the cutoff, and for most applications, this falls well within the limitations of what an architect would want.
All right, thank you. All right, well, we thank everybody for participating today. As you see here on this last slide, if you have any questions concerning the acoustics, please go ahead and contact the Noise Control Group at noisecontrol@price-hvac.com. You will be receiving an email shortly after the presentation, and it will include your PDH quiz along with today's presentation slides. You will also be receiving an email within the next week, and that will include the recording of today's presentation along with some additional resources. And again, my name is Tina Carroll, and if you have any questions, please feel free to contact me at tina.c@price-hvac.com. And we also have some additional webinars that are coming up, some architect webinars. So if you're interested in that, please go ahead and visit our website and go ahead and sign up. That will conclude today's presentation. Thank you.